Section. Introduction. We're going to talk about large language models, LLMs, which have shown some impressive abilities. They can follow instructions given in natural language, use various tools, and even perform some types of abstract reasoning and planning. So far, we've been able to improve these models by giving them feedback on their outputs. But as these models are used for more complex tasks, like writing and executing computations described in natural language, it becomes harder to provide direct feedback. This is where we need new methods for scalable oversight, which involves both humans and AI models interacting to provide high-quality feedback. Let's consider an example. Imagine using a language model to draft a law or a legal contract. These documents are written in natural language, refer to real-world concepts, and require human judgment to interpret their meaning. Even a single character in these documents can have significant real-world consequences. To train a language model to write such high-stakes documents, we need to be sure that every part of a very long document is correct. But having human experts read an entire law or contract produced by a language model to provide feedback is clearly too expensive. So, we need to come up with methods for training and oversight that make efficient use of human judgments. One approach to this problem is to use interactive proofs, a concept from complexity theory. The idea is to train powerful models that behave as we want them to, even though they're only supervised by much more limited verifiers. For example, the AlphaZero model was trained to a superhuman level in the game of Go through self-play, even though no human player could instruct it on what move to make next. This was possible because it's easy to verify who won at the end of a game of Go. Applying this approach to training LLMs requires a method of verifying that the computations produced actually solve the intended task and are executed correctly. This is where the concept of interactive proofs comes in. In computational complexity theory, it's been shown that a verifier with limited computational power can correctly judge the outputs of a much more powerful prover. For example, any computation that can be done in polynomial space, and potentially exponential time, can be verified by a polynomial time verifier interacting with an unlimited prover. This is known as the IP equals PSPACE theorem. Furthermore, for any problem with solutions that can be verified in polynomial time, one can efficiently encode the solutions in such a way that they can be verified by reading only 3 bits chosen randomly from the encoded solution. This is known as the PCP theorem. Recent work has introduced the concept of doubly-efficient interactive proofs, where an untrusted prover is asked to run some computation, and the goal is for a verifier to interact with the prover to accurately judge that the computation was performed correctly. The time spent by the verifier is much less than the time to run the whole computation. However, all these methods from interactive proofs theory apply only to tasks with mathematically precise definitions. But when training a model to follow human intent, the main source of feedback is human judgments of model outputs. Interestingly, when computations are allowed to access a black box, the main theorems regarding the power of interactive proofs are actually false. But we can still achieve efficient verification of powerful provers with access to black box judgments by having the provers compete. We introduce the theoretical model of doubly-efficient debate, where 2 provers compete to convince a much more efficient verifier of the correctness of a computation that depends on access to black box judgments. Our results show that, for any problem whose solutions can be verified by extensive human reflection, the solutions can also be verified with a constant amount of human judgment and interaction with competing provers. However, the models must be able to produce extensive natural language reasoning traces to solve the problem, in such a way that careful human analysis could have been used to judge that the reasoning was correct. These findings pave the way for training models with human feedback via self-play, as even very complex computations described in natural language can be verified by querying human judgments for only a single step of such a computation. Section Summary. Large language models, LLMs, have shown impressive capabilities, but providing direct human feedback for training on complex tasks involving reasoning and planning is challenging. To address this, a new approach called Scalable Oversight is proposed, which combines human and AI interaction to provide high-quality feedback for training and oversight of complex AI systems. The theoretical model of doubly-efficient debate is introduced, where 2 competing provers use black box human judgments to convince a verifier of the correctness of a computation. This model allows for the verification of complex computations using only a constant number of queries to human judgment. Section. Our results. Let's break down our findings. We've developed a concept we call doubly-efficient debate. This is a formalized way of training two AI models to compete against each other in solving a computational problem, with the aim of convincing a verifier, who has access to human judgments, that their solution is correct. The main objectives are twofold. First, we want the model arguing for the correct solution to convince the verifier without using significantly more computational effort than it would take to solve the problem on its own. Second, we want the verifier to rely on a fixed number of human judgments, regardless of the computational effort needed to solve the problem. Think of it like this. If the models were drafting a legal contract, this method would allow us to provide feedback on the entire contract by showing only a small, fixed number of sentences to a human evaluator. This makes it possible to train these models on a large scale. We've proven that this method works in several different scenarios. For starters, we've shown that it works when human judgments are modeled as deterministic, and the competing models are given clear instructions in natural language. We've also extended these results to situations where human judgments are stochastic, or random. In addition, we've proven that our method works when the models are asked to propose a solution themselves and then justify its correctness with a natural language argument. We've even formalized this theorem using the Lean-4 theorem prover. Our work builds on previous research, such as the debate proposal by OpenAI, which suggested setting up natural language debates between AI models judged by humans. However, our model of doubly-efficient debate advances this concept by providing debate protocols where the honest prover always has a winning strategy that can be implemented in polynomial time, even when the dishonest prover has unlimited computational resources. We've also drawn inspiration from the concept of doubly-efficient interactive proofs in computational complexity. This model was originally designed to handle situations where a verifier wants to delegate a polynomial time computation to an untrusted prover, while spending much less time to verify that the computation was performed correctly. Our protocols can be seen as a type of process-based feedback, where two AI systems compete to convince a limited verifier that a given outcome has been arrived at by a reasoning process that the verifier would endorse. In terms of safety, there have been various proposals that directly supervise language models with human feedback, as well as with additional data from external sources. There are also alternatives to debate as approaches to scalable oversight, including recursive reward modeling and iterated amplification. We've also explored the use of Turing machines with input and an oracle, which is a function that provides answers to queries. In the context of language learning models, LLMs, the Turing machine represents a set of natural language rules and instructions, and the oracle represents human judgment along with any other external black box feedback the model may receive. We've defined languages in terms of complexity classes and provided definitions for deterministic and probabilistic oracle Turing machines. For LLMs, these languages correspond to problems that can be described in natural language, each with a yes or no answer that may depend on human judgment or other black box feedback encoded by the oracle. In conclusion, our protocols are strongly connected to the idea of process-based feedback, where the goal is to directly supervise the reasoning process of an AI system, rather than just the final outcome. This is particularly important for safety and scalable oversight, as it corresponds to the case where the LLM proposes a plan in natural language, and goes through a potentially long sequence of steps to argue that execution of the plan will have the desired outcome. Section Summary. The authors introduce the concept of doubly-efficient debate, which is a training setup where two AI models compete to convince a verifier, who has access to human judgments, of the correctness of a solution to a computational problem. The goal is to design protocols where the model arguing for the correct solution convinces the verifier without expending much computational effort, and the verifier's queries to human judgments do not grow with the computational effort required to solve the problem. The authors prove theorems achieving this goal in different settings, including when human judgments are deterministic or stochastic, and when the models propose solutions themselves and provide justifications. Section. Debate. Let's discuss a concept called a debate. A debate involves three main components: a set of oracle Turing machines, an oracle, and a common input. The Turing machines are divided into two categories: provers and a verifier. The provers exchange messages in a series of rounds, and all parties can read these messages. The verifier, at the end of each round, processes the information and gives an output of either 0 or 1. This setup also allows for the provers to take turns by alternating empty messages. Now, let's talk about a specific type of debate called a doubly-efficient debate. This type of debate varies depending on the computational power and limitations of the provers and the verifier. In this setup, the provers and verifier operate within specific time constraints and the verifier makes a certain number of oracle queries. A debate protocol can decide a language with a certain level of completeness and soundness. In terms of completeness, if a certain condition is met, then for all oracle Turing machines, the debate with the oracle and input satisfies a specific requirement. In terms of soundness, if a different condition is met, then for all oracle Turing machines, the debate with the oracle and input also satisfies a specific requirement. In a deterministic scenario, where there is no randomness, the honest prover always wins. However, in a stochastic scenario, there needs to be a constant gap between the completeness and soundness, which can be amplified by repeating the protocol multiple times and taking the majority outcome. A debate protocol outlines the behavior of honest provers in both scenarios. It also requires that the honest prover wins the debate with a higher probability while operating within the time constraints, against any strategy by the dishonest prover. This requirement formalizes the intuitive idea that debates should be structured so that it's easier to tell the truth than to lie. In a doubly efficient debate, both the time constraints for the provers and the verifier are polynomial in the length of the input, and the verifier makes a sublinear or ideally constant number of oracle queries. Now, let's discuss how this debate concept relates to training and inference. In our theoretical model, both the provers and the verifier have access to an oracle representing human judgment. The prover's access to the oracle represents the pre-trained model's extensive knowledge of human judgment, which continues to grow throughout the training process. The verifier's access to the oracle represents actual judgments made by human raters. During training, the pre-trained models are trained via self-play to win the zero-sum game given by the debate protocol. When a model queries the oracle, it uses either pre-trained knowledge or knowledge gained during self-play to predict the answer that a human would give to the oracle query. When the verifier queries the oracle, it corresponds to asking an actual human rater to judge an oracle query. The distinction between pre-trained knowledge for provers and queries to human judgments for the verifier is critical. This is because the training cost in terms of the number of queries to human judgment equals the number of verifier queries to the oracle. As long as the number of verifier oracle queries is bounded, the training procedure can scale to arbitrarily complex computations by the models, while still only requiring a bounded number of human judgments. During inference, when a model is asked to solve a problem or follow complex natural language instructions, the debate protocol is still run. However, no human feedback is used. Instead, the output of one model is trusted, as long as the other model does not abort or point out a flaw. Section summary. In a debate protocol, a verifier interacts with two provers through message exchanges over multiple rounds. The protocol aims to decide a language with completeness and soundness properties, ensuring that the honest prover wins with higher probability against any dishonest strategy. In the context of training and inference, the debate protocol involves access to an oracle representing human judgment, where pre-trained models use their knowledge to predict human responses, and the verifier queries actual human raters. Section. Deterministic debate. We're going to discuss three types of debates: deterministic, cross-examination, and stochastic. In a deterministic debate, we can solve any problem that can be solved in a limited space, with the time taken by the verifier being almost linear to the space used. This is done with a constant number of verifier queries. If we have a language that can be decided by a specific type of machine, an oracle Turing machine, within a certain time and space, then we can use a deterministic debate protocol to decide that language. The details of this are in the proof section. This concept can be compared to doubly efficient interactive proofs, where there's only one prover and no black box oracles. It's been shown that any computation that uses a certain amount of time and space can be decided by a doubly efficient interactive proof in a certain amount of time. However, it's still an open question whether this can be improved. The protocol for this type of debate is a bit complex and relies on previous work in interactive proofs. It doesn't apply when there's a black box oracle. The protocol for this deterministic debate is given in a specific section. The basic idea is to have one party output a supposed middle configuration of the computation. Then the other party decides to recursively call the protocol on either the first or the second half of the computation. This recursion ends at a single transition of the machine, which can be checked by the verifier. In a cross-examination debate, we can increase the power of the debate by allowing for cross-examination, where multiple copies of each debater are questioned independently. This should give more power, as the independent copies must give consistent answers to the queries asked, making it harder for them to lie. In this type of debate, the verifier can query independent, non-communicating copies of both parties. The verifier isn't required to read the entire transcript of the debate, but can selectively query a subset of the transcript. This type of debate can decide any problem solvable in polynomial time, using only a certain amount of verifier time, and only a certain number of oracle queries. The protocol for this type of debate is simple and powerful. One party outputs the whole transcript of the computation, the other party outputs the location of a supposed mistake, and the verifier checks only this location. In a stochastic debate, we give a debate protocol for any language that can be decided by a probabilistic oracle machine with access to a stochastic oracle. This oracle is intended to model human judgment, as well as other types of responses from nature, like real-world data or observations. However, access to a stochastic oracle introduces an additional subtlety, where small changes in the oracle's distribution may add up to a significant difference in the final output probability over the course of a computation. To account for this issue, we require an additional assumption for the machine. For this type of debate, we have a language that can be decided by a probabilistic oracle Turing machine within a certain time and with oracle queries of a certain length. Then there is a debate protocol with cross-examination that can decide this language with a certain level of completeness and soundness. The protocol for this type of debate is given in a specific section. The protocol describes the prescribed behavior of the honest provers, but emphasizes that dishonest behavior may occur. The protocol proceeds in rounds, where in each round one party proposes a probability distribution over the next bit given the computation so far. Then both parties use cross-examination to engage in a coin-flipping protocol in order to sample the next bit of the computation from the distribution proposed. Finally, one party can abort the protocol at any round, whereupon the verifier samples from the oracle in order to check if the proposed distribution at that round is correct. This type of debate delivers non-trivial savings in verifier time and query complexity whenever a certain condition is met. In particular, the most interesting case occurs when a certain value is a constant independent of the computation time. Section Summary. Deterministic debate with cross-examination can decide problems solvable in bounded space with verifier time that is nearly linear in the space used, and only a constant number of verifier queries. The protocol is complex and relies on prior work in interactive proofs, but it does not apply in the presence of a black box oracle. On the other hand, stochastic debate introduces a debate protocol for languages decidable by a probabilistic oracle machine with access to a stochastic oracle, where changes in the oracle's distribution can affect the final output probability. The protocol requires an additional Lipschitz-Ness assumption for the machine and delivers savings in verifier time and query complexity. Section. An example for THM. Protocol stochastic. Let's imagine a scenario where a researcher is interested in conducting a meta-analysis on the impact of caffeine on learning among college students. The researcher outlines a plan to achieve this, which includes searching for relevant studies, selecting those that meet certain quality criteria, and conducting a statistical analysis using a random effects model. The researcher also plans to measure the variability between the studies using meta-regression. This plan is similar to a machine in our theoretical model. Some steps in the plan, such as determining whether a study has a clear flaw, require human judgment. In our model, this is where a human judgment oracle comes into play. To execute the plan, a model is prompted to follow the instructions, while meticulously documenting everything relevant to show that the instructions are being followed correctly. For instance, it might include text from each study to explain why it was included. Another model will scrutinize each step taken by the first model and may stop the process if it believes a mistake has been made. Let's say the second model stops the process when the first model decides not to include a particular study. The protocol requires the first model to estimate the probability of a human agreeing that the study has a clear methodological flaw. If the first model's estimate is close to the actual fraction of human raters who agree with it, the first model wins. If not, the second model wins. We have formalized this theoretical model using Lean4 and Mathlib, a mathematical library for Lean. Our algorithm has a few differences from the original model, such as using external randomness and different constants. We use two monads, prob A and comp SA, to formalize the debate protocol. Monadic syntax is great for expressing stochastic algorithms, and working over finitely supported distributions avoids the need for integrability side conditions during proofs. We also consider a scenario where the models can produce a polynomial-sized witness for the membership of an element in a language. In this case, the models are required to run in polynomial time when given the witness as input. This corresponds to a situation where a model proposes a solution to a complex problem and argues for its correctness via a polynomially long natural language argument. As long as this argument can be verified through extensive human reflection, there is a debate protocol that allows a human judge to only check a constant number of steps of the argument when interacting with two competing models. We have theorems that follow from this protocol. For instance, there is a debate protocol with cross-examination that can deterministically decide the membership of an element in a language given a witness. There is also a debate protocol with cross-examination that can decide the membership of an element in a language with a certain level of completeness and soundness, given a witness. The proofs of these theorems are provided in a separate section. Section Summary. In this section, the authors provide an example of a high-level plan in natural language for conducting a meta-analysis on the effects of caffeine on learning in college students. They explain how the debate protocol works, where one model carries out the plan while another model examines each step and can potentially abort if it believes a mistake has been made. The authors also mention the formalization of the protocol using Lean4 and Mathlib, and discuss the scenario where debaters can produce a polynomial-sized witness for the membership of a language, showing that there is a debate protocol that allows a human judge to check only a constant number of steps of the argument. Section. An example for THM-MA debate. Let's illustrate the concept of a debate with a witness using a simple example. Imagine a scenario where we don't have a pre-established plan, unlike the example we used to explain the stochastic protocol theorem. Suppose a researcher poses the question, does caffeine enhance learning in college students, and requests a comprehensive plan to answer this question. The researcher also asks for a detailed explanation of why the plan is valid, and then proceeds to implement it. In this context, the comprehensive plan and its justification serve as the witness, which is a term we used in our machine-assisted debate theorem. This witness is produced by a machine, which we'll refer to as machine 3. Machine 4, on the other hand, follows the instructions given in natural language, which are implied in the researcher's request. Its task is to meticulously review each step of the plan and its corresponding justification to ensure its validity. Once it confirms the plan's correctness, it executes it. However, to carry out Machine 4's tasks with the witness, it's necessary to make several calls to the human judgment oracle, which we'll call Oracle 20. The protocol then continues in a similar manner to the previous example. Machine 3 guides Machine 4 through each step, while another entity, which we'll call Entity 6, is ready to halt the process if it identifies a step as incorrect.